Hello everyone, welcome to my video on gas laws. In this video we're going to talk about three things, the properties of gases, some units that we use to measure gas pressure, and then I'm going to introduce a few different gas laws. So let's start first with the property of gases. Let me share my screen with you. All right, so we'll start with the properties of gases. When we talk about gases, we need to remember way back from the very beginning of the semester when we were looking at just how is a gas different from a solid. Those were our two extremes. And then we would compare how close the particles were together, whether or not they would take the shape of their container. And so I'm just wanting to remind you, think back to the properties of just the gases. Remember that the particles, they have a tendency to spread out. So the molecules which make up a gas will fill any container. So if it's a round container, you're going to have a completely round gas. If you have a square container, you're going to have a square gas, so to speak. It's the property of gases that their particles have a tendency to spread out, and they'll completely fill whatever container you put them in. Because there's so much space between the particles, you can easily push the particles back together, or you can easily compress a gas. So that's what we mean by compressing them, is literally pushing the particles back together. In order to compress the particles or to push them back together, you have to exert some force on them to do so. And here, when we start talking about gas laws, we'll kind of revisit this idea about filling a container and being compressible. When you have two gases, two different gases, they have a tendency, given enough time, to completely mix with each other. So gases are not so much like when you have a solid mixed with another solid, or you might have different chunks of solid mixed in with another solid. Gases have a tendency to completely mix with other gases. So it is possible to have a solution, and gases usually form homogeneous solutions where everybody's just completely in the same phase. A good example is air. Air is not a gas, it's actually a mixture of gases. Most of what we breathe in as air is nitrogen, roughly about 80%. The other component of air is oxygen, about 20%. And then the remaining small percentage that's left, when you mix nitrogen and oxygen to make gas, most of our air is just that. But the other small percentage is going to be water, a little bit of carbon dioxide, some ozone, some methane, and all the other gases which we find in the atmosphere. When you put gases in a container, they are eventually going to exert pressure on their container. So if you have a container with a gas in it, those particles inside the container are eventually going to hit the walls of their container. And when they hit the walls of their container, they will exert a force, which we would interpret as pressure. If we're talking about air, like all of the particles that make up the atmosphere, we'll see that what we find is that air actually makes up atmospheric pressure. And I'll give you an example of what I mean. So again, when we talk about pressure, let's say you have a container, like a tank where you put your propane in. Those of you that have propane tanks for your homes or maybe for your farm vehicles, propane is usually a liquid, but it can turn into a gas. Or if you put natural gas, we'll use that, it's methane inside of a container, those particles are going to completely fill the container, and eventually the particles are going to hit the walls of their container, and when they do that, they're going to exert a force right there at the spot where they hit the container, and we interpret that force as gas pressure. But if we're talking about the surface of the earth, talking about the surface of the earth, remember that our air is a mixture of gases. So it could be molecules of water or molecules of carbon dioxide or molecules of nitrogen. But the earth exerts gravity on everything. including those particles that are above the Earth's surface. So even though these particles in the air are not actually in a container, they are eventually going to hit the Earth's surface. When they do that, they're going to exert pressure because you're going to hit the surface of the Earth with a force, but that's not the same as when you have pressure due to an enclosed container. Because this is the particles that make up the atmosphere, so to speak, these are atmospheric gases that are striking the Earth's surface, exerting a force. We call that force atmospheric pressure. So atmospheric pressure is just the gases found above the Earth's surface, which are striking the surface of the Earth due to gravity pulling them in. And this is really what keeps our atmosphere in place, is gravity acting on the atmosphere itself. Let's talk about some units of pressure. Go back to my PowerPoint here. Let's talk about some units of pressure and how would we measure these units of pressure. So if we are talking about measuring atmospheric pressure, the name of the device that we use to measure atmospheric pressure is called a barometer. This is a very early invention. It was invented by Evangelista Torricelli, and so this is referred to as a Torricellian barometer, and it's made by taking a long test tube, basically a really long test tube, and filling it completely with liquid mercury, and then turning that liquid test tube upside down and allowing the mercury to flow into a glass dish, so that any mercury that leaves that upside down test tube is going to leave behind not a pocket of air, but a vacuum. And the story goes, or the legend, is that Evangelista Torricelli took this device with him everywhere he went, and he would measure the column of mercury inside of the glass test tube. And what he found was that when he was near the ocean, or what we'd call sea level, the height of the column was 760 millimeters of mercury. This became a standard unit, or what we later called a standard atmosphere of pressure. Now, if you are measuring the pressure of a gas inside of a container, the device that you use to measure gas inside of a container is called a manometer. So a barometer is for measuring atmospheric pressure. That's what the weatherman uses. A manometer is a device using for the pressure of a gas inside of a container. So I've got here on display two different gauges. If you notice the first gauge, at the very bottom you see PSI, that stands for pounds per square inch, which is one set of units that we use to measure pressure inside of a container. The next one over actually has two different units. The outer larger black numbers, those are in inches of mercury, and then the red numbers on the inside of the dial, those measure in bars. You're familiar with a manometer. You probably just don't call it a manometer, but the most common manometer that you and I usually come into contact with is a tire pressure gauge, because basically your tire is a closed container, and when you measure the pressure of the air inside of your tire, you're measuring the gas pressure inside of a closed container. So when you use a tire pressure gauge, you're using basically a hand manometer. Now, I mentioned units of pressure, different units that we use to measure the pressure of a gas. And just as a reminder, pressure is a force that the gas particles exert. So when the molecules of a gas strike either the inside of their container, or if we're talking about atmospheric pressure, when the molecules of our atmosphere strike the surface of the Earth, when they physically push on the surface, then they are exerting a force. And so pressure itself is defined as force over a unit area. And so if we are measuring pressure of a gas in standard units or using the metric system, the unit is actually the Pascal, because pascals takes into account force in the unit of newtons, and areas is always a two-dimensional measurement. So if you measure area in one direction with a meter and then measure that area in another direction with a meter, you would have meters squared. So 1 Newton divided by meter squared is equal to 1 Pascal. Even though that is the standard unit, it is not one that we commonly use. The one that we actually have a tendency to use are equivalents to standard atmosphere. Hello, I'm back. So we were talking about what are the units that we use to measure pressure. So let me see here. Let me go back to my screen share. So the standard unit or the metric unit for measuring pressure is a Pascal. What we're going to be using for gas laws, not so much the Pascal, but we're going to be using the standard atmosphere. That's what it's called. That doesn't mean it's a standard unit. It's just called a standard atmosphere. And the definition of a standard atmosphere is based on the Torrid Chilean barometer measurements. So if you remember, I mentioned that when the instrument was taken to sea level, the height of the mercury column was 760 millimeters of mercury. That unit was defined as being 1 atmosphere of pressure. So when we refer to anything as being a standard atmosphere of pressure, that is 1 ATM, that's the abbreviation for atmosphere, or anything equivalent to it. There are 4 other units that you should know, and you should know their equivalents to 1 ATM. So 760 millimeters of mercury, that is also equivalent to 1 atmosphere. They're equal to each other. 760 torrs, named after, you guessed it, Evangelista Torricelli. Back to the standard unit, 101.5 kilopascals, that is the equivalent to 1 atmosphere pressure. And 17.7 pounds per square inch, or PSIs, is also equivalent to 1 atmosphere of pressure. So now I'm going to talk to you about the 5 different gas laws that I'll expect for you to be able to use to solve different gas law problems. Now, for the gas laws, I'm just going to present them right now. I'm not going to solve any sample problems in this video, but I'm going to introduce the gas laws, what you should know about them, and then at the end of the video, I'll talk a little bit more about how to practice solving problems using the gas laws. So the first gas law that I'm going to introduce to you is Boyle's law. Boyle's law is typically written like this: P1 V1 is equal to P2 V2. Now, how this is interpreted, it's basically if you increase the pressure of a gas, you decrease the volume of a gas. In other words, it's an indirect relationship. An indirect relationship means that when one goes up, the other one goes down. This is true if you keep 2 things constant: number of moles and the Kelvin temperature of a gas. So just so that you know, gas laws typically relate pressure, volume, number of moles, and Kelvin temperature. So when you see our gas law written, and it's only using 2 or 3 of these values, whatever doesn't appear in the law, you know that it's being kept constant. So that's something that you should know for the upcoming quizzes is you need to know not just what is the gas law, how it's written, but how do you interpret it? Is it a direct or indirect relationship? And what is constant or what is unchanging about that gas law? What you'll see in the next video are going to be some sample problems using Boyle's law, especially under changing conditions. Usually this is condition 1 and this is condition 2. Again, I'm not going to solve any problems here on this video. Instead, I'll introduce the gas laws. Okay. The next law is Charles's law. And for this one, the law is written like this: volume 1 over temperature 1 is equivalent to volume 2 over temperature 2. For this expression, the relationship is not going to be between volume and temperature. It's going to be between volume and temperature. So the relationship is that when you increase the temperature, you also increase the volume. So if the arrows or the change is happening in the same direction, that's actually a direct relationship. So when one goes up, the other one goes up. It also means if you decrease the temperature, you decrease the volume of a gas. It is important that you remember for Charles's law that temperature is in kelvins. And just as a reminder, Kelvin is degrees Celsius plus 273.15. So it's an easy conversion, but you cannot put a Celsius temperature, you can't plug it in here and end up with the right answer. So again, the third thing you need to know about the law itself is what is being kept constant. So if these are the variables that we usually worry about, this one has volume and temperature. So that means that the two that are not mentioned, pressure and N, which stands for number of moles, that's what's going to be kept constant. In other words, this law is true if the pressure and the number of moles don't change. Again, this law is used under changing conditions. The third law I'm going to introduce is Gay-Lussac's law. Gay-Lussac's law. And let me rewrite this here so we kind of keep up with it. And for Gay-Lussac's law, it's written like this: pressure over temperature under one set of conditions is related to pressure and temperature over a second set of conditions. So for this law relating pressure and temperature, it's also a direct relationship. It says basically when you increase the temperature of a gas, you also increase the pressure of a gas. Or it could be if you decrease the temperature, you decrease the pressure. Again, when the arrows go in the same direction, that is a direct relationship between the pressure and the temperature of a gas. As a reminder, for gas laws, our temperature is never in Celsius, it's always in kelvins. So if you are solving problems, again, if you input a Celsius temperature here, you won't end up with the correct answer. The last question is, what must be kept constant or what is unchanging for this gas law to be true? Well, pressure and temperature both appear in the equation. So that means that volume and the number of moles, or the amount of the gas, is not changing. So volume and number of moles are constant. Two more laws. Two more, I promise. Two more laws. Next is Avogadro's law. Avogadro's law, it relates number of moles and volume. The relationship looks like this. N1 over V1 is equal to N2 over V2. So this is a first set of conditions. This is a second set of conditions. Again, we're assuming that we're working under Kelvin temperatures. Let's fill in this side of our notes. What this relationship says is that the more number of moles or the more gas you have, then it's going to take up more space. So the more moles, the more volume. Vice versa, the fewer moles, the less volume. So that, again, you're probably already saying it in your head. It's a direct relationship between number of moles and volume. You probably are ahead of me in guessing which things are unchanging or which variables remain constant. Number of moles and volume appear in the equation. So that means that the two variables which don't change in order for this law to be true are pressure and temperature. And just as a reminder, it's always Kelvin temperature. Always Kelvin temperature. One more law. One more law. The last law that I'll introduce is called the ideal gas law. Oops, I don't know if you can hear my dogs barking. Hold on. Let me see why my dogs are barking.